Hello, my name is Mike Simons with Abode Energy Management. Today I have the pleasure of presenting to you Heat Pump 101 training for Mass Save Energy Specialist. During today's presentation, we'll be doing an introduction of how Mass Save sees the role of heat pumps in the Massachusetts marketplace. We'll do an overview of the technology. We'll discuss all the different equipment options, whether that's an air source heat pump, a ground source heat pump, or an air-to-water heat pump. We'll discuss operation and maintenance that a homeowner should be aware of before adopting the technology, and then we'll also review all of the rebates and resources that Mass Save is providing to make this project a reality. To get started with an introduction, Mass Save is a partnership between local electric and gas companies as well as energy efficiency service providers. Together, there's a common goal of helping residents and businesses save money and use less energy and leading our state into a clean and energy-efficient future. As many of you know, Mass Save recently was able to adopt a new 3-year plan, and the goal of the new 3-year plan, as always, is to reduce emissions and also to continue to make Massachusetts a national leader in the clean energy economy. One new change with this 3-year plan is there's not only a continued effort of decarbonization, but there is going to be a real effort in the electrification of heating and cooling systems. Before we start getting too deep into the technology, I wanted to highlight some big picture items that everyone should be aware of. Number one, we need to dramatically reduce the amount of carbon going into our atmosphere, and heat pump technology is an excellent way of doing that when tied to our grid. Second key concept is energy specialists, and the recommendations that you make can have a huge impact on how appropriate a heat pump system is for a home and whether or not the adoption of that can be affordable. We'll explore more on that later. Number 3. Heat pumps today can provide 100% of a building's heat load down into single digits, potentially even down into negative temperatures. The technology has improved and it's appropriate for our region. Number 4, a lot of homes have comfort issues, and a heat pump system that is properly designed can address a lot of those problems. Last year, the Boston Globe ran a really great series of articles regarding some of the challenges that the state is facing in regards to the adoption of air source heat pumps. So there's a pretty sensational headline, and I certainly don't want to beat anyone up over this, but some of the key quotes that I thought were interesting in the article is that, some homeowners and contractors affiliated with Mass Save dissuaded them from removing their fossil fuel systems and going all electric. And another good quote is, some residents said that they sought to convert their homes off of fossil fuels. Contractors, including those associated with Mass Save's energy audit program, told them that heat pumps alone could not heat a home adequately throughout a Massachusetts winter. And then the last quote is that the customer who wanted to install heat pumps needed to go through 5 different contractors to actually find one contractor who was able to help them fully remove their fossil fuel-based system. With looking at this slide, I want to highlight a few things. There's 3 different houses. Each of those houses have 3 different heating loads. So the one on the left-hand side, when it's 2 degrees outside, it needs 100,000 BTUs per hour to properly maintain 70 degrees inside. The house on the right-hand side would need 24,000 BTUs to properly be able to maintain 70 degrees. If we look underneath it, we'll see that there's 2 different types of heat pumps, a traditional heat pump and a cold climate heat pump without a capacity drop. If I were to be thinking about the house in the middle, which requires 50,000 BTUs per hour, and I was putting in traditional heat pumps into that home, I would see that I would need 4, possibly 5 heat pumps to be able to meet 100% of that building's heat load. Because at 5 degrees, that heat pump only has 12,000 BTUs, the home needs 50,000 BTUs. So it would be coming up short. So, whether you need 4 or 5 would likely depend on whether or not your attic can benefit from air sealing and insulation, or maybe there's some windows that could be changed out, or maybe a rim joist that could be properly air sealed and insulated. All of those measures would be able to bring the heat load down by way more than 2,000 BTUs. If I'm looking at the heat pump on the right, which is the cold climate heat pump without a capacity drop, I would see that I would only need 2 of those heat pumps to be able to meet 100% of the building's heat load. So it's not so much that the heat pump isn't right for our homes or isn't right for our climate, or that homes can't get heat pumps, or that only energy efficient homes make sense for heat pumps. You just need to select the right equipment for the building. You may be asking yourself now, well, how do you know if a home needs 100,000 BTUs or 50,000 BTUs or 24,000 BTUs per hour? The answer is there is a software or a calculation called a Manual J heat load report. In that report, you would go and measure all of the walls, all of the windows, the level of insulation in the attic, the insulation along the floor, how leaky the home is, and you put all of those inputs into a calculator, and it will tell you exactly how many BTUs per hour the home will need for its heating load as well as for its cooling load. For this home, when I put all of that information in, I found that the heat load for the home was 108,000 BTUs per hour. Now, if I were to be going down into the basement and I were to look at the steam boiler, I would see that the steam boiler has a heating output of 129,000 BTUs per hour. So the heating system is greater than the heat load. The steam heat works in this home. Now, let's just go and think about how mass save and heat pumps may correlate with this type of a home. For this home, even though it was listed at 108,000 BTUs per hour, you do not need to design a heat pump system for 108,000 BTUs per hour. First, you should always insulate and air seal. So instead of having uninsulated walls, packing those walls full of insulation. Instead of only having 3 inches of insulation in the attic, getting it up to code minimum. Air sealing everything that's possible. So around the rim joists, up in the attic, the knee walls, the slopes, really just making sure that the home is no longer having catastrophic air leakage. And then also upgrading the windows. The home had single pane with storms, upgrading them to an Energy Star window, or even better, a triple pane window. When all of those measures became implemented in this home, instead of needing 108,000 BTUs per hour, the load of the home dropped all the way down to 47,450 BTUs per hour. And if I were to be looking at heat pump equipment, I could find that there is a multi-zone heat pump from a major manufacturer. It's 1 outdoor unit. It can support up to 8 indoor units. It has a max capacity of 54,000 BTUs per hour. I want to highlight some key takeaways. Number 1, if a home needs 108,000 BTUs per hour versus 47,000 BTUs per hour, all of your operating costs, your heating expenditures, are also going to be a level at 2x what the home would now be performing at. Another takeaway is that the install cost is going to be 2 times more expensive. So with this type of a heat pump project with 1 outdoor unit, 5 indoor units, supplying 100% of the heat load, that type of a project ranges somewhere around $20,000 to $25,000. Well, if we were doubling the amount of equipment, now it's a $40,000 or $50,000 project. The last key takeaway that I think is important is we do want to electrify and decarbonize HVAC, but we also have a lot of other goals, or a homeowner may as well, like decarbonizing their transportation carbon impact. So if you're putting in lots of heat pump equipment, you may be missing out on opportunities to be able to decarbonize other appliances without needing to invest in upgrading your electrical service. So less equipment means less operating costs. It also means that the home's more future-proof for other decarbonization goals. Now we'll do an overview about heat pump technology. How do heat pumps work? Well, it depends who you ask. So if you're asking a sales consultant, they would likely say, wonderful, better than you could ever imagine. It's the best way to heat and cool your home. Because I am having the opportunity to speak to energy specialists, I will be slightly technical. So if you go back to building science training, you may remember that as you increase temperature equals increase pressure. And if you decrease pressure, you will decrease temperature. And a quick example of that, if you take a can of compressed air and you spray it and you release the pressure in the can, decreased pressure equals decreased temperature. So heat pumps are really going to be working off of the same principle. So say that you are in heating mode. There is going to be refrigerant going from an indoor unit to an outdoor unit. As the refrigerant is leaving the indoor unit and going outside in the winter time, there will be a component that will release the pressure on that refrigerant. And as the pressure drops, it is going to become wicked cold, like negative 30 degrees cold. So even if it's 0 degrees outside, there is a massive amount of energy in 0 degree air compared to negative 30 degree refrigerant that's inside of a copper tube. Hot goes to cold. The energy in that 0 degree air is going to get absorbed into the negative 30 degree refrigerant, and eventually that refrigerant, if enough air passes over it, will become 0 degree refrigerant. Now that 0 degree refrigerant is going to be brought inside. A ton of pressure is going to be applied to that refrigerant, and instead of it being 0 degree refrigerant, now it's 80 degree refrigerant or 90 degree refrigerant. 70 degree air from the home passes over it, and now it's 71 degree air or 72 degree air. Or if the air inside was originally 68 degrees, now it passes over it and it's going to be 70 degree air. And then the refrigerant then flows back to the outside, the pressure is released, it's wicked cold again, and the process happens again and again and again. And that's how a air source heat pump works. And in the summertime, it just works in the reverse. It just pulls the heat from the inside or pulls the energy from the inside and it dumps it on the outside. The exact same way a window AC works, the exact same way a central AC works, the exact same way your refrigerator works. It's just taking the heat from inside of the box, which could be a house or could be a refrigerator, and it's dumping it to the outside, which could be the outside or it could be into your kitchen. So the refrigeration process is used all over. Now, while we do have this slide up, I do also want to just highlight two different things. So anytime that you're thinking about an air source heat pump, there is always going to be two visible components. On the outside, you'll have the outdoor unit, which some people still refer to as a compressor, but it works in reverse. And then you also have the indoor unit. In this picture, it is a wall-mounted ductless mini split. But there is a handful of different types of heat pumps that we'll be reviewing today. So we haven't yet talked about why a heat pump is so much more efficient than other types of heating systems. So let's do that now. So say if you were to buy 1 gallon of fuel or 1 therm of fuel, and you were to put that 1 unit of 1 in a heating system, depending on the efficiency of the heating system, you're not going to get out the full unit in heat to the home. So a lot of that energy in an older heating system may be going up and out the chimney. Other heating systems may have a lot of jacket losses, and that energy is just being lost to the slab in the basement. That's only part of it, though. There's also distribution losses. And if there's really leaky ductwork, a lot of that heat that the heating system put out never got delivered to the home, Or if it's steam, you're heating up thousands of pounds of steel and cast iron just to move a drop of water from a basement and keep it as a gas all the way up to the living space. So with a traditional fossil fuel-based heating system, you're putting in 1 unit of energy, you may be only getting out about 70% of that heat actually being delivered to the home. Say if instead of using fossil fuels, you used electricity. If you're using electricity as you would to make toast or to dry your hair with a blow dryer or with using an electric baseboard, you put out 1 unit of electricity, you get out 1 unit of heat. And that may seem like it is a lot more efficient. One thing that's true with electricity, though, is it is considered a more expensive form of heat because you're getting the full kilowatt hour of electricity being turned into heat in your home. However, there's transmission losses, there's losses at the power plant, so that's why typically in Massachusetts using electric resistance or just plain old electricity for heat is probably not the right way to go for most homes that is trying to keep operating costs down. Why heat pumps make a lot of sense is they're not using that electricity to make toast or to make heat. They're using that electricity to move energy from one location to another. They're using electricity to harvest energy from outside the home and just bring it into the home. Or they're using electricity to take energy from the home and release it to the outside or deposit it to the outside. So instead of putting in 1 unit of electricity, getting out 1 unit of heat, with most well-designed air source heat pump systems in Massachusetts, you're putting in 1 unit of electricity and you're probably getting out pretty darn close to 3 units of heat over the course of the entire year. And with a ground source heat pump, because underground is a lot warmer than outside in January, the coefficient of performance is a lot higher on that type of equipment. One thing that I did want to highlight, and this may be some of the concerns regarding what some people in the Mass Save world and in the HVAC world have regarding this equipment. And this is true. Well, as the temperature drops, the heat pump capacity doesn't need to drop. And we learned about cold climate air source heat pumps already. But as the temperature drops, the coefficient of performance of the heat pump drops. So if we're thinking about the toaster oven, 1 unit of electricity in, 1 unit of electricity out. With an air source heat pump, when it's warm outside, like 47 degrees-ish warm, it'd be 1 unit of electricity in, almost 3.5 units of heat out. Some heat pumps, that number may be closer to 4, others it may be closer to 3. But by the time you've reached 5 degrees outside, single digits, with this particular heat pump, only 1 unit of electricity in, 2 units of heat out, or a little bit more than that. So do know that as the temperature drops with an air source heat pump, the coefficient of performance drops. However, over the course of the heating season, pretty much any well-designed air source heat pump that would be Mass Save approved probably has an annualized coefficient of performance of somewhere between 2.5 and 3. A question that often comes up is, how much do heat pumps save? And it's actually a surprisingly tricky question to answer because, as you all know, fuel prices fluctuate. The other thing that is not discussed is that different heat pumps have different performance. So one manufacturer may be performing a bit better than other manufacturers. Another thing that's true is that, say, a oversized heat pump isn't going to be running that efficiently throughout the course of the year and will have a much lower coefficient of performance. One thing that I did want to highlight is Mass Save has put together a really great tool to help you as well as homeowners understand exactly what the savings would look like for their home. Let's go explore the output of that. So this is what the output looks like after visiting masssave.com/heating calculator and putting in some information about the home, like the type of fuel that you're using, the type of heating system, the square footage. It lists out all the different types of heat pumps that are available on the market today, and a dollar savings associated with adopting that technology, as well as a carbon savings associated with adopting the technology. It's a really good resource to set some expectations with a customer and have a customer have some expectations of whether or not this equipment has any chance of paying for itself or how it will be affecting their energy expenditures. So I do recommend that everyone explore this. This chart may need a little bit of explaining to do, but I'm going to try my best to help you understand what we're looking at over here. I put this chart together based off of 10 years worth of weather data from the National Oceanographic Atmospheric Association. So I pulled 10 years worth of weather data, and then I just plotted out the count of how many hours we spend at each degree. And that's what we can see in that blue dotted area. So if I'm looking at this, I would see that we really spend the vast majority of our winter time right around 30 degrees-ish. After 30 degrees, or when it's below 30 degrees, there certainly is double-digit hours. There certainly is a few single-digit hours. But by the time that we're in sub-zero temperatures, there's really a non-existent heating load. The number of hours is typically a few hours overnight while people are sleeping. So that isn't really what we're trying to ever design a heating system for, is for an all-time extreme of negative 16 degrees. So when I'm looking at this chart as well, I see a few other colors, and that is going to be kind of the energy expenditures at that degree for all of the different fuels. So with electric resistance, you can see that that one is higher than all of those. And if I'm looking on the y-axis on the left-hand side, I'll see that, at 29 degrees, it costs $160 to heat with electric resistance. But by the time that I'd say for all the 59 degree hours that we encounter over the course of the winter, that's around $50. And if I were to be switching from electric resistance to propane, I would see that kind of at the peak, instead of $160, it may be $100. And then if I'm looking at home heating oil, that's probably about $60. Air source heat pumps, probably $55. With natural gas, like $50 maybe, for kind of the peak at 29-ish degrees. So you can just go and see that, like, the blue line's natural gas, the green line's air source heat pumps, black line's propane. Those are all really pretty tightly grouped together. And the fuel prices that I have were relevant to winter of 2022, like this January and February. So that was when oil was only $3.50 a gallon. But I do have electric resistance at 28 cents per kilowatt, a cost per therm of $2. So it's a pretty tight grouping, no matter whether you're heating with an air source heat pump, home heating oil, or natural gas. Do know that gas is the cheapest when we do look at this chart. But air source heat pumps, they're really not that much more expensive to run than gas. Inverse home heating oil at $3.50 a gallon, it's like above freezing, the air source heat pump's cheaper to operate. Below freezing, home heating oil was cheaper to operate at $3.50 a gallon. But by the time that I'm recording this now, home heating oil is $5 a gallon. So that's what I was talking about with fuel prices. So if you are trying to pick up any messaging regarding like thinking about this, thinking about weather, thinking about falling coefficient of performance, is just know that with an air source heat pump, it's cost competitive to the other fossil fuels. Sometimes it's a bit cheaper, sometimes it's a bit more expensive, but as far as just thinking about cost, it is affordable, it is predictable, just because electricity never has those huge swings that some of the other fuels may have. What that previous chart didn't cover is how carbon intensive all of these different fuel sources are. So if instead of looking at this as just dollars and cents, we're just looking at this as the pounds of emissions that each of these fuel sources or each of these heat sources would be producing over the course of the year, it really is, no matter what temperature it is outside, when you're pairing a heat pump with today's grid, there's going to be significantly less carbon emissions. And one thing that is exciting is our grid is getting cleaner and cleaner by the year, and we have set real targets and real goals, and we will reach real milestones in getting our grid filled with renewables to even lower the amount of emissions that this heating system will produce. And the last thing that I'll just touch on is most homes in Massachusetts do have an ability to be able to have on-site renewables as well. And it could be the homeowner is doing things to be reducing the emissions of their HVAC system even more, or someone could also be exploring competitive suppliers to be buying or purchasing 100% renewables from the grid. So heat pumps, they do have significantly lower emissions today. They'll have even lower tomorrow, and there's things that you can do in the meantime, if motivated, to bring that number down today. So we talked about how much heat pumps save, and sorry it wasn't super straightforward or it had a little bit of nuance to it. As far as how much heat pumps cost, I can be a bit more direct to that. So on average, in Massachusetts, we typically see a ductless mini split being fully installed going for somewhere around $5,000, with most homes needing a few units, dependent on the square footage and the envelope conditions, to meet 100% of the heat load. If you are exploring a ducted heat pump solution, we typically see those coming in with new ductwork installed, coming in somewhere between like $15,000 and $25,000. Some things that could be nuanced about this is that some homes don't need a ductless mini split or a few ducted mini split or a few ductless mini splits. Sometimes there is a combination to get the equipment right to meet the homeowner's goals and to meet the building's heat load. An other thing about cost regarding air source heat pumps is they do use electricity. And if the main electrical panel was originally designed to be 100 amps or 60 amps, there is a real likelihood that there's not going to be enough capacity on that main electrical panel to be able to power an air source heat pump, as well as meet future decarbonization and electrification goals. So sometimes, in addition to buying all of the heat pump hardware and getting it professionally installed, sometimes you are also needing to work with an electrician to upgrade the electrical service coming into the home as well as the main electrical panel. Do know that in 2022, with the Mass Save Heat Loan and the new 3-year plan, electrical costs regarding the adoption of heat pump equipment can also be financed under the heat loan. Some key considerations. Before adopting air source heat pumps, you do want to button up the home as much as possible. Even if you're not going to be adopting air source heat pumps, you want to button up the home as much as possible. It's going to make the home more durable. It's going to make the home safer. It's going to make the home use less energy, save you money, burn less carbon. It makes total sense. To qualify for some of the new Mass Save incentives, like the whole home heat pump incentive we'll talk about in a bit, you need to fully weatherize the home and take full advantage of all of the recommendations that an energy specialist to be able to claim that rebate. Second key consideration is integration with a pre-existing heating system. So, for some homes, it makes sense to go 100% electric. For other homes, it may not be cost effective for them to do. Or maybe they just put in a brand new heating system. Maybe they do have a delightful distribution system with like radiant floors that they absolutely love. Do know that air source heat pumps can be integrated with existing heating systems. And when they are integrated into existing heating systems, controls can be installed so it's seamless. The heat pump runs when it's most efficient. It automatically switches over as the temperature drops to the traditional heating system. And that can work out really well for some homes, and it can be 100% appropriate for other homes. The other thing that to set expectations for, if you were spending $300 on gas, plan for your electric bill to be at least $300 higher. So all of that is just going to be moving over from either a home heating oil delivery company, a propane company, a gas company, over onto the electric side. So do make sure that you are setting the right expectations with a homeowner. I wanted to take a few moments to talk about the different equipment options that are available. The first is air-to-air heat pumps, which is probably the most widely installed type of heat pump that we see in our market. One of the types of air-to-air heat pumps that's widely installed is what's called a ductless mini split, where you have the outdoor unit, and that is going to be connected to a heating system that is located on your wall, as we see on the left-hand side, on the floor, which we see in the middle, or into the ceiling, which is what we see on the right-hand side. Do know that each of these has their pros and cons. With the wall-hung units, they're typically the most economical to install. They're the easiest to install, typically. For floor-mounted units, some of the big benefits of those is you can place them on interior walls and not just exterior walls as part of a retrofit. It's easier to change the filter, and some people would argue that it's a cleaner look. With the ceiling cassettes, those can make a ton of sense when there's an unfinished attic space above you, but it is a lot harder if there is a finished floor above you with trying to get the line sets to the outside. All of these work. All of these can have varying capacities of somewhere between, say, 6,000 BTUs all the way up to 24,000 BTUs on residential equipment. The other type of air source heat pump is what's called a ducted heat pump. And there's really two different types. There's one type that's referred to as slim duct, or sometimes it's called the low or medium static. And that's pretty much the same thing as a ductless mini split without its plastic shell on it. And instead of having a plastic shell, you would be connecting ductwork to it. And typically the amount of CFM, or cubic feet per minute, that these types of equipment can put out, it's really enough to do a room, 2 rooms, possibly even an entire floor. So that's what would be called slim duct, or low static, or medium static. The other type would be called a high static unit, or it could also be called a centralized heat pump. And that type of equipment looks the exact same as an oil or propane or natural gas fired furnace, or what we would see as a traditional central AC, but instead it's a heat pump. And that type of equipment can have capacities of like 12,000 all the way up to 48,000 BTUs per hour. So that's really enough horsepower or BTUs to be able to migrate an entire home off of their fossil fuel-based systems. In addition, with the centralized heat pumps, sometimes they can also have components that can help out with resiliency as well as redundancy. They can have an electric heating element built in that if the heat pump is ever completely covered in snow or there ever is a polar vortex, the electric heating element can kick on and take over. In addition, with ducted heat pumps, they can also be sitting right on top of a oil-fired furnace or a gas-fired furnace. So there is a lot of flexibility with thinking about ducted heat pumps with being a dual fuel type of configuration. If someone is just feeling a little bit nervous about the technology, it still can be an option for that homeowner. For the outdoor units, there's a handful of different configurations. So there's single zones, which are typically the most efficient type, where it's 1 unit outside tied to 1 unit inside. There's smaller multi-zone units where it's 1 unit outside and it can have a handful of units, like 2 to 4-ish, all connected to the one outdoor unit. And then they have these much bigger multi-zone systems where maybe there's a potential for up to 8 outdoor units that are connected to branch boxes that are connected to the outdoor unit. So do know that there's a lot of variety as far as the right number of outdoor units, the type of outdoor units, and how many indoor units that it is going to be connected to. We're now going to go through 3 different examples to kind of work through what ductless design can look like or should look like or shouldn't look like. So we're looking at a very small or a compact 2-bedroom apartment, and we just have one ductless mini split for it all. And we can just say hypothetically the heat load of that space is 18,000 BTUs per hour, and we have in an 18,000 BTU ductless mini split. And it's pretty centrally located. It's blowing down the hallway into the bedrooms. It has that big cathedral area down in the living room that it's picking up. This equipment may seem undersized for some, because I could say that if you have the heat set to 70 degrees in the main living space, it's not going to be 70 degrees into the bedroom. Is it going to be 68 degrees or 66 degrees or 64 degrees? It really depends a lot on the envelope conditions. So, do some people in New England heat their home with a pellet stove or a wood stove and just have one emitter? And some rooms are delightful or hot, and other rooms may be less delightful and cold. It works for some households, but it doesn't work for others. So for a lot of people, I think, who have become accustomed to a central heating system with emitters or distribution in every room, this may be a little bit risky as far as the design goes. But is it enough horsepower or enough BTUs for this home? Certainly, as long as the home needs 18,000 BTUs and this mini split's able to put out 18,000 BTUs. But is every space going to be comfortable? That's a little bit hard to say, and it's also subjective to the homeowner's goals. So now the pendulum has swung in the other direction. The home or the zone or the apartment is still needing 18,000 BTUs. But instead of having one unit to cover the entire apartment, now there's 4 separate units. There's a mini split in each bedroom, there's a mini split in the living area, there's a mini split in the kitchen area. Let's just say hypothetically that all 4 of these mini splits were on one outdoor unit. The size of that outdoor unit for most manufacturers would need to be around 36,000 BTUs, 2 times what the heat load is of that space or of that home or of that apartment. And when it's oversized by that, the equipment will never have an opportunity to run efficiently. It's going to be cycling on and off versus gently modulating up and down to kind of slowly add heat or remove heat from the space or the zone. So we would strongly advise people to be cautious of any HVAC contractor who is talking about putting a mini split into each and every room in the home. Not only is it going to be oversized, it's likely going to be a lot more expensive. And if that's how they're designing equipment, there is a really good chance that these quotes are going to, become unaffordable for a lot of households in Massachusetts. This last example is what most manufacturers would like to see HVAC contractors installing, and this is the type of design that works for a lot of households, where you can balance comfort as well as energy efficiency. The home still needs 18,000 BTUs, and the homeowner would like to have an emitter or a heat source in every single room, so there's not a temperature swing or a temperature delta between room A and room B. Here's a great way to do it. For the large open area, you're putting in a ductless mini split. That mini split could be, say, 12,000 BTUs. And then for the 2 small bedrooms over in the back over there, just putting in a ducted unit and just dropping 2 registers down to each room, and hopefully having 2 returns for each room so everything stays balanced. You could even have a 3rd register also going into the bathroom, and now that space is also going to be properly conditioned. And that system could be a 6,000 BTU unit, and 12,000 plus 6,000, that equals 18,000. Now you're matching the home's heat load. You have emitters in each and every room. And the heat pump system is going to be awesome. It'll be delightful. It'll be much more comfortable than what the homeowner's previously experiencing. And it's going to be using significantly less carbon. And depending on the fuel, there can be some real savings associated with adopting this technology. So this is what everyone would like to see. If I were to have to summarize the key benefits that we just learned about, I think I would bucket them into these 4. Number 1, compared to home heating oil, propane, and electric resistance, there is some real savings to be had with adopting air source heat pumps. The second benefit is it's extremely flexible to install this equipment, whether ducted or ductless or a combination of both. Homes, zones, single-family, multifamily businesses, there's usually a benefit with adopting air source heat pumps, primarily for cooling, but also even on a partial home solution, displacing a lot of the need of turning on your heating system in the spring and the fall time, and also just fixing some comfort issues in the home. Regarding comfort and convenience, you're buying a heating system, but you're also buying a cooling system, and you're also buying a dehumidification system. And one thing that I think is important that we haven't talked about, we talked about carbon, but we didn't talk about climate change. In Massachusetts, we're going to be going on in summertime from an average of 9 days over 90 to over 29 days over 90. Our planet's warming, our region's warming, and it will be nice to have a delightful cooling system in place to keep up with it. And finally, regarding global warming, heating with an air source heat pump, significantly less emissions than heating with other fossil fuels. Cooling with an air source heat pump, they're typically close to double the SEER rating or the EAR rating of what a window AC would. This type of equipment with the multi-zones, they're close to a SEER 20. With some of the single zone equipment, they're a SEER 30. Window ACs would have a SEER rating of 10. Older, like R22 central ACs, it's like a SEER rating of 10 or 12. So there's a huge jump in the efficiency on the cooling side. More efficient equipment, less kilowatt hours bought, less emissions into the atmosphere. It makes a lot of sense. I now have the pleasure of talking to you about a mature technology that's new to our region, which is called air-to-water heat pumps. So with an air-to-water heat pump, instead of taking air from the outside, extracting the energy off of it, bringing that energy to the inside, and blowing air on top of it to extract the energy to the indoors, it's going to be taking air from the outside, stealing the heat off of it, transferring that energy into water, and bringing that inside. And some benefits of heating your home with water versus heating your home with air is it's quieter, which for some people is really nice. Another nice thing about it is, say, the smallest ductless mini split is like 6,000 BTUs. Say it is easy for a hydronic system designer to be putting in 2,000 BTUs worth of low temperature baseboard or a 2,000 BTU radiator. So there's a lot more potential flexibility with design. Another nice thing about air-to-water heat pumps is they can also do domestic hot water. So you're not thinking about a hybrid hot water heater that is potentially stealing heat from the basement when having more heat in the basement may be favorable some times of the year. With air-to-water heat pumps, cooling is also possible. The big issue right now, and why this is new to our market and not widely adopted, is it is heating the water up to around 120 to 140 degree max. Most of our hydronic distribution system is looking for water that's like 180 degrees. So with air-to-water heat pumps, technology here, it's proven, it's mature, but for a lot of homes, the distribution system as is may be incompatible with this type of a heat pump without some sort of retrofitting the plumbing distribution system. So it's starting from left and moving right. There's a few different components of an air-to-water heat pump system. So to start off on the left, that is what's called a monoblock system. What's exciting about this type of a system is all of the refrigerant connections. Everything is already packaged inside of that unit, just like your refrigerator. So any plumber in Massachusetts does have the ability to install an air-to-water heat pump and not need to worry about refrigerant. Say with this system, it would be glycol that's flowing between the heat pump and the thermal storage, which is located inside the home. And this is the same thing as an indirect storage tank. It's just serving as a placeholder for this hot water. From this thermal storage system or buffer tank, it's going over to a manifold. And from the manifold, that's where air-to-water gets really exciting. There's a lot of different ways that you can connect it and configure it. So you can connect it to a radiant floor system. You can be connecting it to a European-style flat panel radiator. You can be connecting it to like a fan coil air handler. That's the same as what you would see with a hydro air system. So with air-to-water, tons of flexibility. You can mix and match different emitters, and you can have the benefits of heating with hydronics, which it's, quieter, less dust, all through an air-to-water heat pump. So it is really exciting. I now want to take a moment to talk to you about ground source heat pumps, which is also referred to as geothermal. However, there's no volcano needed. So to set some expectations regarding geothermal, there's always going to be 3 different components. And sometimes when you're adopting geothermal, you're needing to buy all 3 components of the system. So the first is going to be the outdoor component. And that can be a vertical loop drilled down into the earth like a well, or it can be a horizontal loop where your yard is likely going to be excavated, greatly entrenched, and then there's going to be a loop inside of a pipe that will be carrying a glycol solution from the earth back into the house. Now, that loop is always going to be going to indoor components. And that indoor components can be a water-to-air heat pump. So the glycol solution goes in, that's the water. It's going to extract the energy from it and then blow it into air through a duct distribution system. There's also water-to-water heat pumps, so it could be going to all those same type of low-temperature emitters we talked about with air-to-water, or it could be a combo of the two. So there's a handful of different types of heat pumps that support geothermal applications. And the next part about it is, well, how does that heat now get out through the rest of the home? So most common is going to be going through ductwork, the same way a furnace or central AC would. It could be going through the low temperature hydronics, or it could be also going through like a mini split type of a system, a ductless type of a system, or a fan coil type of a system. So there's a lot of flexibility in distribution with geothermal as well. If we remember earlier in the presentation, we had that slide that was talking about coefficient of performance and how it changes as the temperature drops. And compared to like a toaster oven, whereas 1 unit of electricity in, 1 unit of heat out, and then at 47 degrees is like 1 unit of electricity in, 3.5 units of heat out, and at 5 degrees is 1 unit of electricity in and only 2 units of heat out. With a geothermal system, if we're just looking at this chart on the left-hand side, it's like, well, 50 degrees underground is warmer than 47 degrees outside. Does a geothermal system just always run at the best coefficient of performance that a air source heat pump system does? And the answer is more or less yes. So geothermal systems are a lot more efficient. They do have a significantly higher coefficient of performance over the course of the entire heating season than an air source heat pump system does. What is tricky sometimes about a geothermal system is there are some variables that are unknown, including the soil conditions on the property, including the pumping cost of moving the fluid around. So with geothermal, it is 1,000% worth exploring if you do have a good site condition for the technology. And the site condition really is, can you fit a fire truck onto your lawn? And if the answer is yes, then geothermal could be a real possibility. I wanted to talk about some of the realities in our market that make geothermal cost competitive compared to traditional fossil fuel-based systems, as well as air source heat pumps. So to start things off, there is a 26% federal tax credit. This is the same tax credit that makes solar PV make sense for a lot of households. As long as you have the tax liability, 26% of that project you're going to be getting back in terms of not needing to pay federal taxes for that amount. The next thing is with the Department of Energy Resources here in Massachusetts, they also have an alternative energy certificate program, which are referred to as AICs, and that is going to be a mechanism that is going to help bring the project cost down. Massachusetts has a flat $15,000 whole home incentive for adopting geothermal. MassSave, in addition, allows you to finance up to $25,000, 0% interest over the course of 7 years with adopting a geothermal project. And Massachusetts also eliminates the need to pay sales tax on this type of equipment. So with all of these things in mind, it does help make geothermal projects a lot more affordable. But to set some expectations about pricing, as I'd mentioned earlier, there's 3 different components: outdoor ground loop, indoor heat pump, indoor distribution system. For some households, they are needing to buy all 3. For other households, maybe they're needing to buy 2 because they already have a ducted distribution system. It could be a furnace down in the basement, or maybe it's a central AC that's coming down from the attic and hitting all floors. So do know that with geothermal, it's worth exploring, especially with this last part. My big concern with my own mini split equipment that I installed in my own home is that I think that the lifespan of the equipment is the same as any high efficiency heating system, 15 to 20 years. What is exciting with geothermal is the duct distribution system will be there for 50 years or 100 years. You've all seen ductwork as old as that. The ground loop is also not going anywhere for 50 or 100 years. So there is a capital investment that is being made to purchase a geothermal system, but I do think that it is going to be future-proofing the home with having a brand new distribution system, having brand new ground loop, and then come 20 years later, you are just now needing to replace just the indoor heat pump and none of the other distribution system or the outdoor ground loop. I now wanted to talk about some operation and maintenance regarding heat pump equipment. So, number 1, use your heat pump year-round. It's going to be more efficient than anything else in your basement or up in your attic. Number 2, set it and forget it. So just find some number on the heat pump, whether it's off of the handheld remote or if it's off of a centrally located thermostat, just set it and forget it. Heat pumps work best and have the ability to work most efficiently when they're not running in max mode. It's just, if they can just gently add a little heat into the building, or remove a little heat from the building, everything works better. And the home's going to be more comfortable and you're going to use less energy. So avoid setting it back at night or when you go home from work, go to work unless it's for comfort. Keep your filters clean. This is true with any forced air system, but if the filters are gunked up, the equipment's going to be working harder than it needs to. Make sure that if you are going with a ducted distribution system, that all of the ductwork is air sealed and insulated. And that's something that very well could be part of your scope of work as a home performance contractor, as an energy specialist, or as an independent insulation installer. With the outdoor equipment, it's going outside. In New England, we have all 4 seasons, and all 4 seasons have their own quirks. So in the fall time, make sure it's free and clear of leaves. In the springtime, make sure no vegetation's growing around it. And in the winter time, make sure that there's no snow that's building up. That's building up around it. And then the last thing is, like any large investment, if it's a new car, you'd likely be getting it a tune-up, on a somewhat regular basis. With a heat pump, it is a major investment. It is worth making sure that it's well maintained, it's performing properly. So do work with your installer on setting up some sort of annual maintenance, with just making sure that it's always able to run at its peak efficiency. Earlier, I'd mentioned that there is a way to integrate a heat pump into an existing home's mechanical system or distribution system. So I wanted to explore that because it is a little nuanced as far as what Mass Save is looking for and what they're, not really looking for as far as what type of equipment to incentivize or what type of projects to incentivize. So let's just say, for example, that you wanted to just put in a heat pump to meet 100% of the cooling load. So let's say that the heating load's 50,000 BTUs, the cooling load's 30,000 BTUs. So you just want to put in 30,000 BTUs worth of heat pump equipment. You have no incentive or no reason to want to migrate 100% of the building's heat load off of the traditional system because it's only a few years old, or because gas is cheap, or because it's tied to a radiant floor that you really like. I wanted to just highlight some examples of when integrated controls are appropriate and when they make sense and when they're eligible, and when maybe the scope of someone's heat pump project needs to change to be able to claim this rebate, which is $1,250 per ton. So I just want to go through a few examples and figure out whether or not a air source heat pump and the dual fuel or integrated control rebate would be appropriate for each of the different types of homes and setups. So in this bottom left-hand example, we have a single boiler serving a 2-story home. If you were just putting in a heat pump, a ductless mini split on the first floor, that could likely work if it is home heating oil or propane. As that unit is dumping heat into the first floor, that warm air is rising and migrating up to the second floor, that setup could potentially work for a homeowner. If it's just installed on the second floor, that hot, warm, buoyant air is not migrating down. The first floor is still going to be calling for heat. Second floor is going to be emitting heat because it's not on its own zone, and that heat pump's never really going to be running. So Mass Save isn't going to be incentivizing that type of a job. So if you did want to put in a mini split upstairs primarily for cooling, and with the idea of displacing some of the heat in the bedrooms, you would need to then incorporate a unit on the first floor as well to make this type of equipment have a chance of meeting the goals of that program. If we're looking at the home to the right, we would see that instead of having one centrally located thermostat, now there's a thermostat for the first floor, a thermostat for the second floor. Either of those two zones could be swapped out for a heat pump, and integrated controls would work great in that application. If we now look at the home on the top right-hand side, we'll see that there's a central boiler heating the whole home and a central AC that's cooling the second floor. Let's say that we were to be swapping out that central AC and putting in a central heat pump. That central heat pump would likely not, if it just has distribution to the second floor, would not be a good candidate for integrated controls, because the first floor is still going to be calling for heat, the baseboards in that space is still going to be releasing heat, and the heat pump that would be up in the attic would never have an opportunity to be running down to 30 degrees as the minimum. If we were to look at the home on the bottom left-hand side, we would see that it's a central furnace. If we were to put a heat pump on top of that central furnace, that would work for integrated controls. the heat pump would be running down to 30 degrees or lower, or it'd need to run down to 15 degrees of propane. And after that, the heat pump would turn on, the fossil fuel-based furnace would kick on, and everything would still work in that application. Now for the home on the bottom right-hand side, at the time of this recording, I want to just talk briefly about one of the nuances regarding integrated controls. So integrated controls, to receive that rebate, it needs to be integrated into a fossil fuel-based heating system. So say, for example, you wanted to swap up that furnace with central AC up in the attic with a sole source, cold climate heat pump. That type of equipment is not currently eligible to receive the integrated control rebate because there's nothing to integrate into. It's just a standalone heat pump. So if you did want to go with a ducted system up in the attic to replace the unit that's up there, you may need to think slightly bigger about the scope of the project and pursue the $10,000 whole home heat pump rebate to make this project work. So there is a little bit of nuance about how these rules are written, and it may be requiring you to think a little bit differently about the project. But do know that's not necessarily a conversation that you need to have with the homeowner. It is up to the HVAC contractor to help the customer navigate some of the nuances over here. During this presentation, I've talked about some of the rebates that Mass Save is offering, but let's explore those in a bit more detail. Right now for rebates in Massachusetts, this is the landscape. If you adopt ground source heat pump to meet 100% of the building's heat load, it's a flat $15,000 rebate. If you're pursuing air source heat pumps for the whole home, it's a $10,000 rebate. With the existing heating equipment, to be able to receive the $10,000 rebate, it can get ripped out of the home, it can get decommissioned, or you can sign off on that you're not going to be using the equipment unless in case of an emergency. And an example of an emergency would be like a snowpocalypse or that a board goes bad. And do know that if the existing boiler is also your domestic hot water heater, that is not going to prevent you from receiving the $10,000 whole home rebate. The only nuance with it is that you do need to have enough heat sources throughout the home for it to really meet this whole home incentive. So you don't need to have a mini split in every single room, but you do need to make sure that all of the equipment is going to be able to meet 100% of the building's heat load, and that is up to the HVAC specialists to determine. And then there's the integrated control rebate, which is $1,250 per ton, which as long as it's integrated into the existing heating system, into the existing thermostat, that's going to work out well for a lot of households that aren't ready to go all electric. To receive the whole home heat pump rebate, which is the $10,000 one, the criteria for receiving it is 1, you need to decommission the heating system or agree to not use it ever again. The second piece of nuance is all customers do need to start with a Mass Save energy audit, and they do need to implement any recommendations that energy specialist has made. And after the work is completed, that's when they can apply for the rebate. To receive the partial home heat pump rebate, there's a little bit of nuance to it. So the first nuance is if you're heating with propane, the set point that the integrated controls or the thermostat needs to be at is 15 degrees. So say if you're in heating mode from 15 all the way to 70 or 69, that is going to need to be covered by the heat pump. And for 15 to potentially negative 15, that could all be done via propane. With oil and natural gas, that number is moved up to 30 degrees. So from 30 degrees to 69 degrees, that's covered by the heat pump. From 30 degrees below, that's covered with home heating oil or natural gas. Do know that especially with oil at over $4 a gallon, it would make a lot of economic sense to move that balance point way lower. And for natural gas, just because it's set at 30 degrees doesn't mean if the goals of the project aren't related to reducing emissions, that maybe the thermostat should also be set at a lower temperature for the integrated controls. The last piece of nuance regarding integrated controls, if the existing fossil fuel-based system has a non-programmable thermostat or a programmable thermostat, it is very likely that that thermostat is likely going to need to be upgraded to a smarter thermostat that is either Wi-Fi connected or supports multiple heating stages to make it integrate with the heat pump technology. This is not going to be a job of the energy specialist to determine whether or not a piece of equipment meets Mass Save's minimum efficiency standards, but do know that all heat pump equipment that's going in that is rebate eligible, there are specific standards that it needs to meet regarding its minimum heating efficiency, its minimum cooling efficiency, and kind of the flexibility of the heat pump at its rated capacity. So if it has like 100% of its capacity at 47 degrees, does it still have 100% of its capacity at 17 degrees or at 5 degrees? So that's kind of what one of the requirements is looking at as well. For ground source heat pumps, they have their own minimum efficiency requirements as well, and it is kind of determined by the heat pump's design. In addition to Mass Save providing really great rebates and financing for heat pump technology, they are also providing some additional resources for homeowners. These include Find a Contractor tool to find contractors who have the right certifications, have been through the manufacturer's training, and understand the rebate process. And they also are offering no-cost consultations to homeowners who are interested in exploring heat pumps and don't know where to begin. The URLs to both of those services are outlined below. I wanted to finish off on this note because this training is targeted directly towards energy specialists. So, our climate's changing, and so isn't the Mass Save program. Say, for example, with the Mass Save program, you would put in LED bulbs. And there is a general question like, are TCP LED bulbs the best LED bulbs on the market? Is this the right bulb for every fixture for every homeowner? And the answer is probably no. Maybe someone wants Philips Hue dimmable LED color changing bulbs, and that's what works for them. So there is something about being an energy specialist and having a tool in your toolbox as far as recommendations go. So say with cellulose insulation, is cellulose insulation the best insulation? And it's maybe. It depends on the application. Like, it is wildly low embodied carbon. If you get enough inches, it's a startling high R value. You can get assemblies too, but is it always the best insulation or always the right insulation for every single home in every single application? No, probably not. But does it work for the vast majority of Massachusetts households? Is it, affordable to install? Does it have a significant impact in homeowners' operating costs? Is it safe? Is it non-toxic? It's like, yes. So I do think that as we are thinking about heat pumps and we are thinking about energy specialists and your role in the Mass Save program, is whether or not believe that a air source heat pump or a ground source heat pump is the best way to heat in every single home, in every single application. It's like, that's 100% subjective, and you're all allowed to think however you want. But at the same time, the new reality with the Mass Save program is we need to dramatically reduce the amount of carbon emissions that's going into the atmosphere. To do that, we need to migrate people off of fossil fuel-based heating systems as quickly as possible. And after that, we still have a lot of other things to decarbonize. So I do think that it'll be really important and valuable and align your audit with the program goals with stepping into every home and thinking that there's a heat pump opportunity. Maybe it is one ductless unit downstairs and you're not needing to turn on the heat until December. Or maybe it is a ductless unit upstairs and a ductless unit downstairs, and now you have a delightful cooling system upstairs, and now you also still don't need to turn on the heat until December. So I do think that it would be beneficial for everyone attending with just going into every home and not just thinking, how can I help insulate this home, but thinking, how can I help electrify this home and motivate this customer to be migrating away from fossil fuels. It's a great opportunity. There's a lot of important work for us to do, and I do really thank you all for listening into this presentation. Pleasure, and I hope to see you all around.